Hello everyone, welcome back to the channel. In this episode I will be taking a detailed look at the DJI remote controller, the model RC231. I will show its internal architecture and identify the key components on its mainboard. I will analyze the radio frequency transceivers that handle drone communication, the antenna switching networks, the microcontroller that processes the control inputs, and the power regulation stages that keep the whole system running. As a bonus, I will provide the diode measurements of all test pads, which can help you in troubleshooting this mainboard. If you are into PCB analysis or you want to repair a controller, this video can provide you with more background information. Please be aware there are no schematics of this controller available. This analysis is based on my experience, findings and measurements. If the information I provide is wrong, please correct me in the comments below. I also want to say a huge thank you to all of you, my subscribers, everyone watching these videos, and especially those of you who supported me by buying the PDF. Because of you I was able to put that support straight back into this channel. And honestly, this movie is the result of that. None of this would have been possible without you, so from the bottom of my heart, thank you. If you gained any value from this video, consider giving it a like or buy this PDF presentation. It helps me to grow the channel and create more content that you enjoy. And don't forget to subscribe to the channel for more in-depth analysis like this one. So, let's start. You need a controller for the DJI Mini 2 drone because it serves as the primary interface between you and the drone, allowing you to fly it. The controller connects to the drone by radio signals, giving you real-time control over its movement, the altitude and the camera functions. This is the left stick. Moving the left stick up or down changes the altitude of the drone. It is also known as a throttle stick when you move it up and down. Moving the left stick to the left or right controls the orientation of the drone. This left and right movement is also known as a yaw stick. This is the right stick, and moving the right stick up or down changes the pitch of the drone. This stick is also known as the pitch stick. Moving the right stick to the left or right changes the roll of the drone. This stick is also called a roll stick. In the center, the flight mode switch is located. Toggle this switch to select the desired flight mode. The C mode stands for Cine mode, the N for normal mode, and the S for sport mode. The left button is also known as a flight pause or return to home button. Press once to make the drone brake and hover in place. If the drone is performing a quick shot, a return to home or auto landing, if you press it once, you can exit the procedure before braking. Press and hold the return to home button until the remote control beeps to start the return to home function. Press this button again to cancel the return to home and regain control of the drone. This FN button is the customizable button. To customize the function of this button, go to the system settings in the DJI Fligh app and select control. This button here is the power on or off switch. Press once to see the battery status. And if you press and hold this power button, it will power on this controller. Here you can see the top view of the controller. So on the left side we have the customizable button, the FM button. On the right side we have the photo video toggle button. So this is the FM button. And this is the video and photo mode toggle button. On the top of the controller we can find the gimbal dial. The gimbal dial is used to control the tilt angle of the drone's camera in real time. On the right side you can find the shutter and the record button. The shutter record button has two functions depending on the drone's current camera mode. In the photo mode, if you press it, it will take a photo. And in the video mode, if you press it, it will start and stop the video recording. In this location the USB-C connector is located. If you connect your mobile to this USB-C port, you can see the live view from the drone. This is the main board of the DJI controller, and this is the front side. In a DJI controller, the left and the right joystick are analog input devices. They use 2-axis potentiometers based gimbals for pitch, roll and yaw and throttle. So each joystick has 2 analog axes. So combined they have 4 analog signals. The gimbal dial is connected to this connector in location 3. It adjusts the tilt of the gimbal, so it moves the camera up and down. On location 4 there is a serial flash memory located. This chip is a NOR flash IC and it stores the firmware, so the main operating system of the controller. So it includes the bootloader and the application code. And it's all stored in this NOR flash IC. On location 5, this chip is a fuel gauge IC. It's a CW2015. This chip is designed for Lipo batteries. It measures the cell voltage and the temperature. Then it calculates the state of charge, also known as SOC. This controller used 2 Lipo batteries. To report the battery status, like remaining charge and when to recharge, this fuel gauge IC will provide this information. One Lipo battery is connected at this connector at location 6. The other Lipo battery is connected at location 7. On location 8, the USB-C port is located. This USB-C port is used mainly for charging the controller's internal batteries, so for the Lipo battery on the left side and the Lipo battery on the right side. This USB-C port is also used for firmware updates, so when this mainboard is connected to the computer, it can update the firmware in this NOR IC. On location 9 we have the speaker. The speaker is basically there to give an audible feedback and warnings, so you don't have to rely only on your mobile phone. So if the controller wants to send feedback to the user, it will create a sound at this speaker. The shutter and record button will be connected at location 10, so this is the connector for the shutter record button. If you are in the photo mode and you single press this button, it will capture a photo. If you are in video mode and you press it once, it will start or stop the video recording. This is the flight mode switch, and with this flight mode switch we can select the scene mode, the normal mode or the sport mode. The scene mode is mainly used for smooth filming. The normal mode gives a more balanced flying. In the sport mode you can control your drone faster, but it's less safe because the drone reacts fast on your commands. On location 13 the power button is located. So this connector is the USB-C port for the phone. And this is the primary connection to your phone or tablet. So the video signals, the control signals between the drone, the controller and your mobile phone will go through this connector. You can also update the firmware by your phone. The firmware will be sent to this NOR IC and it will be executed here. On location 15 the battery level LEDs are located. If you press the power button once, the LEDs will turn on. The 4 LEDs are solid. The Lipo battery is about 100%. When there are 3 LEDs solid, it means that the battery is at 75%. When there are 2 LEDs on, it means that the Lipo battery is at 50% of charge. If there is 1 solid LED, it means that the Lipo battery is at 25%. If 1 LED is blinking, it means that the battery is critically low, so you have to charge it immediately. On the DJI RC-N1, also known as the RC231 controller, there are 2 antennas. These antennas are located in region 16. These antennas will provide the communication or the connection between the controller and the drone. OcuSync is a DJI's digital transmission system. It is used in many of their drones to send video and control signals between the drone and the remote controller. This link carries control signals, so your stick inputs, and video feed, live camera view from the drone. The controller constantly listens on both antennas. It automatically uses the antenna with the stronger, cleaner signal at any moment. This reduces interference and dropouts, so especially in areas with Wi-Fi noise or obstacles. This is the backside of the mainboard, and in location 8 we have the USB-C port. In area 17 we have the power management IC. This power management IC is called the BQ24259, and this chip is responsible for charging the battery. It's also a power switcher, so it chooses between the USB and the battery to power the system. So it can charge the battery, but it can also deliver the power from the battery to the system. And this chip is also responsible for regulating the voltage. So it will create a power rail that's also known as a sys pin, and this power rail will go through the whole mainboard to different components. In this area the components are located that are responsible for the signal transmission. There are 3 main components located here. First is the Leascore IE1000, and this chip is used in the OcuSync digital transmission system that DJI uses. This chip here is a 5.8 radio frequency front-end transceiver. It handles both power amplification and low noise amplification. So this chip is responsible for sending and receiving a clear transmission and reception of the signals. In area 21 there should be a chip located. In this picture the chip is missing, that's because I was repairing this mainboard. The chip here is a QPF4550. This chip is a 5 GHz power amplifier that will boost the signal strength before the transmission, so it will amplify the signal before it goes out from the antenna. Basically, this chip is responsible for communications over Wi-Fi and especially for the Wi-Fi 6 systems. So this is an amplifier. On area 22 we have a similar chip, that is the QPF4206. This is also a 5 GHz power amplifier that also boosts the signal for the transmission. Because we have two antennas and we have two different frequency bands, so each chip will amplify the radio signals that is sent to the antenna for each frequency band. In area 23 we have a +5 buck controller. So this is a voltage regulator that will create the +5 volt that will go to different components on the mainboard. In area 19 we have the S1 chip, and this chip is used for the drone communication. It is responsible for a good data connection between the drone and the controller. In area 20 is the Cortex ARM processor, so this is basically the brains of the whole operation for the controller. This Cortex ARM processor handles the processing of control signals from the joystick and other components like the buttons, and is responsible that these commands are translated into commands that the drone understands. And this chip is also responsible for the power management, the battery monitoring and the firmware execution. This is the global overview for the most important components that are in the controller. At the core of the controller is a microcontroller unit, also known as an MCU, which is a low power ARM Cortex microcontroller. This microcontroller handles sensor input processing like the joystick, the buttons and the dials. It's also responsible for signal packet creation, so the flight control instructions that will go to the drone. It's also responsible for the USB connection with your smartphone. The microcontroller also handles the OcuSync encoding and decoding of messages that comes from the drone, or the commands that has to be sent to the drone. So these commands will be encoded and decoded using the OcuSync method. The microcontroller reads the firmware that is stored in the Winbond 25Q128 flash IC, and the microcontroller reads this firmware and start executing commands. All the control signal that comes from the joystick, the buttons, the dials will go to the microcontroller. So each joystick has two axes, X and Y, creating 4 channels. So we have pitch, roll, yaw and throttle. When you move the joysticks will output an analog voltage, and the voltage is between 0 volt and 3.3 volt. And this signal will go to the microcontroller. It will go through a 12-bit or a 16-bit analog to digital converter to give the analog signal a value and convert it into a digital value. These chips here that are located in area 19, 18, 21 and 22 and the antennas. This circuit is responsible for sending the commands to the drone and also receiving the video downlink. These commands are transmitted over a 2.4 GHz or a 5.8 GHz frequency band. The system constantly scans for the interference and hops between those two frequencies. All the data signals that has to be sent or the data signals that has to be received will go to this communication processing chip, the EA1000. Once the communication processing is done, it will go to the signal processing, the S1 chip. On area 8 the USB-C port is located, so you can charge your drone by connecting a USB-C cable to the port. And it also will negotiate with the power management chip, the BQ24259, what the power of this V-bus power rail should be. Once this negotiation is done, it will start charging the battery. So 3.6 volt is needed to charge the Lipo batteries. Then this power management chip will start generating different voltages. So like 3.3 volt that will go to the buck controller. And then we have the +5 volt that will create the 5 volt for the mainboard. For the 3.3 volt it will go to the flash memory chip. It will go to the Cortex MCU microcontroller, to the communication processing chip and the S1 signal processing chip. For the 5 volt it will go to the power amplifiers and also to the fuel gauge IC, the CW2015, that is located here. So the communication processing chip is a dedicated radio frequency transceiver chip. It handles modulation and demodulation of the signal. And then it will go to the S1 for signal processing. These two chips are also known as a low noise amplifier and power amplifier, and is used to boost the signal to the antenna to the drone. When the live feed video is received by the controller, it will go through these power amplifiers. It will go to the communication processing chip. From there, it will go to the signal processing chip. It will go to the microcontroller. And from the microcontroller, the video signal will be sent to the mobile phone. This is a USB-C communication port. And from here, the video control signals will go to the mobile phone. The camera feed from the drone is compressed into a camera feed that uses the H.264 or the H.265 protocol. And this video signal is sent back to the controller using the OcuSync. And the controller receives these signals and passes this raw video back to the mobile phone. When you press and hold the power button, the power management chip will start regulating the power rails. The bus voltage or the system voltage will be generated from the batteries. So it will get the power from the battery. This power management will start regulating the power rails and will create the different power rails and also the system voltage or the bus voltage. Then the microcontroller will start reading the firmware from this flash memory and it will boot up. Then the MCU will start different self-tests like checking the battery voltage, scanning the joystick positions, verifying the internal memory integrity, and will also check if there is communication possible to the USB-C ports and also if the communication is possible with the mobile phone. The microcontroller will also check the radio frequency chips if there is communication possible between those chips and the microcontroller. Then the input initialization starts. So all components like the joystick, the switches, the dials are pulled. These control signals, analog signals, are read by this analog to digital converter that is located in the microcontroller. After that, the joysticks are calibrated. The next step involves radio pairing using the OcuSync 2.0. That is the DJI custom digital transmission protocol. The controller starts scanning the 2.4 GHz and the 5 GHz frequency bands using its dual band radio frequency transceiver in location 18. After that, the controller is looking for a beacon signal that comes from the drone's onboard radio. Once the controller hears the drone identification broadcast, it will perform a handshake with the drone and the controller. When the handshaking procedure starts, the controller and the drone are checking the session keys, and this is needed so that the commands that you send won't get hijacked or heard by other devices. So it's a security feature. The command signals are broadcast using two antennas for better range. And once those radio signals are transmitted, the drone's radio module will get those signals and will start decoding the commands. At the same time, the drone is capturing live video and it compresses it using the H.264 codec. It will stream it back using OcuSync. The controller will receive this stream. It will pass it through to the USB-C communication port, and from there it will go to the mobile phone. In the next slides, I've published known good diode measurements, and these diode measurements are marked in red. The voltages marked in green are voltages, and values marked in purple are resistance measurements. If you compare these values with a faulty board, you can try to isolate the problem. So if you have a broken board, you can measure these points and compare it with these values to try to isolate the problem. To measure these diode voltages, you have to put the multimeter in diode mode. You set the red probe to ground, so it can be so you can put it on a ground plane. The black probe is the probe that you put on the test bed. The value that is given in the multimeter is the voltage drop, and this voltage drop you can compare it with these known good values. If the component reads a different value, this component or the components near this test bed are faulty. Please be aware, if you compare these values, there can be a tolerance of plus minus 10% deviation on the value. The analog signals from the left and right joysticks will go to the microcontroller. The microcontroller will convert this analog signal to a digital signal. The conversion will be done by an analog to digital converter. It is located inside of this microcontroller. After that, the microcontroller will interpret these digital signals and will convert them to commands. It will send it to this signal processing chip, and from the signal processing chip, it will go to a dedicated radio frequency transceiver chip. Then it will go to these two power amplifiers. These signals can be sent by using the 5 GHz frequency band or the 2.5 GHz frequency band. And from that, it will be transmitted to the drone. When the drone receives this signal, it will demodulate the signal, it will interpret this signal to a command, and then the drone will execute the command. The signals from the left analog joystick will go to this connector. From this connector, the signals will go to the microcontroller. So when we zoom in, this is the connector which the left joystick is connected to. The left analog stick on the controller controls the yaw, that's the left or right rotation, and the altitude, that is the up and down movement of the drone. When you move the left analog stick, it generates an analog signal. These analog signals are converted into digital signals by an ADC, analog to digital converters, and that is located within the microcontroller. So the microcontroller converts the analog signals to digital signals. The microcontroller then will process these signals and it will be translated into specific commands for the drone, such as adjusting its yaw or altitude. From the microcontroller, these commands are sent to the drone via the OcuSync digital transmission system. To summarize, the left analog stick signals are going to the microcontroller. The microcontroller will convert these analog signals into digital signals, and it will convert these digital signals to commands. And from the microcontroller, these commands are executed and transmitted to the drone. And from the microcontroller, these commands are transmitted to the airwaves to the drone. From there, the drone will interpret these commands and it will adjust the ESC, so the electronic speed controller, to adjust the 4 motors. The right analog joystick signals will go to this connector on the right side of the mainboard. These signals will go to this connector, and from this connector the analog signal will go to the microcontroller. The microcontroller will convert these analog signals to digital signals. It will interpret these commands into commands that will be sent to the drone, and then the drone will execute these commands. The red values are the diode measurements, and you can compare each test pad with this known good value and compare them with your value. If you see a big difference in voltage, that can indicate a problem, and that's the area where you can troubleshoot. The same applies to the right analog joystick. You can compare these known good diode measurements with the values that you measure on your mainboard. If you see a big difference, so that can indicate a problem area. The same applies for the gimbal. So the gimbal signal will go to the microcontroller. The microcontroller will convert this analog signal to a digital signal. It will interpret this signal and convert it to a command. It will send it to the signal processing chip. From there it will go to the power amplifier. From here, this signal will be sent over the 5 or the 2.5 GHz frequency band, and it will be transmitted to the drone. The gimbal dial control signal will go to this connector in location 3. This signal will go to the microcontroller, and from the microcontroller it will be sent to the S1 chip, and from the signal processing chip it will go to the radio frequency transceiver chip. From here it will decide which frequency band to send the signal. So it can be sent using the 5 GHz frequency band or the 2.5 frequency band. And from here it will go to the antennas. And the antennas are located here. So one is for the 2.5 GHz and one is for the 5 GHz. The gimbal dial is connected to this connector in location 3. These are the diode measurements for the data lines. And these signals will go to the microcontroller. The gimbal control signals manage the orientation and stabilization of the drone's camera. What will happen is when you adjust the gimbal using the controller, so if you tilt the camera up or down, the controller sends this control signal to the microcontroller. These control signals are transmitted wirelessly from the controller to the drone. The microcontroller will interpret these signals and convert them into commands for the gimbal. And then the gimbal motors executes these commands by adjusting the camera's orientation. The firmware for the controller is stored in this WinBond flash memory chip. So the microcontroller reads this firmware and it will start executing the program. The memory chip is located at location 4. This chip stores the firmware, which includes the software instructions needed for the controller to operate. When the controller is powered on, the firmware stored in this flash memory is loaded into the microcontroller. The microcontroller will execute these firmware instructions and it will start doing some different tasks like signal processing, the communication, control functions. When you update the controller's firmware, this firmware will be stored in this chip. In red are the known good diode measurements, so compare them with your board to see if there is any problem near this circuit. So basically the firmware that is stored in this flash memory chip will communicate with the microcontroller. So the microcontroller and the flash memory chip are connected together. This chip here, the CW2015, is a fuel gauge IC. A fuel gauge IC is an integrated circuit. It will measure and monitor the state of this battery that is connected. This chip will monitor the state of charge of this battery, also known as SOC, also the state of health, SOH. It will measure the voltage, the current and the temperature. The purpose of this chip is to give information about how much energy remains in this battery. The chip can prevent unexpected shutdowns, it improves the battery performance, and protect the battery against overcharging, deep discharging or overheating. This chip will measure the battery voltage and current. It will communicate with the power management chip and also with the microcontroller. The fuel gauge IC is located in area 5. And this chip will measure the voltage and current from the batteries that are connected to these two connectors. This chip will send and receive data from the microcontroller. So it will send and receive data from the microcontroller. And it will also communicate with the power management chip. When we zoom in, this is the fuel gauge IC, also known as a CW2015. It is designed for lithium-ion batteries. This chip will also measure the stage of charge of the battery, also known as SOH. And will measure the voltage of this battery using a current sense resistor. Somewhere on this board there is a current sense resistor. So this fuel gauge IC will communicate with the microcontroller and the power management chip using the I2C interface. This fuel gauge IC can also send an alarm and an interrupt signal to the microcontroller. So in a case that the battery reaches some pre-programmed threshold, let's say it's overcharging or it is under voltage, it will alert the controller that there is something wrong. So it will start communicating with the microcontroller. So when the microcontroller receives this alert signal, it can execute some specific program. Most likely it will send warnings and you will see it on your screen, like battery not okay or under voltage or land the drone now. The main power comes from the two Lipo batteries, and this battery will provide power to the power management chip. The battery will deliver power to the power management chip, and this chip will start generating different voltages. Also, this power management IC will charge this battery, and the voltage of this battery will also be measured by the fuel gauge IC. There are two Lipo batteries connected, one on location 6 and one on the connector on location 7. This is the Lipo battery that can connect to this connector at location 6. This is the other Lipo battery and it will connect at location 7. This Lipo battery is an 18650 cell. It can deliver power up to 7.6 volt, so between 7.2 and 7.6 volt is normal. This USB port can be used for charging the battery, and it can also be used for updating the firmware of the controller. The USB-C port is located here in region 8, and this is the backside of this USB-C port. Near the USB port there are some components located, so most of the time you can see some capacitors and inductors. Those will be used for smoothing the voltage and filter noise from the USB power line. There's also some fuses or PTC resettable fuses. It will protect the circuit from overcurrent. And in this case we have also an ESD protection diode, so it will protect the board from static discharge on the USB lines. On the front side, these components are most probably DP-DT analog switches. So this is an electronically controlled two-way switch for two signals. It let the circuit choose between two different analog paths. So these switches are controlled digitally. The speaker is located in area 9. This speaker is basically here to give you some audible feedback and warnings, so you don't have to rely only on the screen of your phone or tablet. This built-in speaker is not used for playing audio or drone sounds. Instead, it provides system alerts like startup or shutdown tones, connection status beeps, warning alerts, and button feedback beeps. The signal for the shutter record button will go to the microcontroller, and the same story applies here. It will convert it into commands, it will go to the signal processing chip, and then it will go to the radio frequency transceiver chip. And from there it will be transmitted over the 5 GHz frequency band or the 2.5 GHz frequency band, and then it will be transmitted to the drone. The shutter record button is located in area 10. And the signal for the shutter record button will go to this connector. From here it will go to the microcontroller. The shutter record button is a user input switch that triggers the camera to take photos or start-stop video recordings. The signal is for the flight mode, also for the flight pause or return to home button, and the power switch will also go to the microcontroller. The flight mode switch is located in area 11. Then we have on area 12 the flight pause return to home button, and in area 13 we have the power button. All these signals will go to the microcontroller. The flight mode switch is a manual input switch that changes the drone flight behavior or control mode. When the switch is in the center, it's the normal flight mode. And these are the diode measurements when the switch is in the normal flight mode. In location 12 we have the flight pause or return to home switch. And these are the known good diode measurements. When you press and hold this switch, the drone will automatically return to its recorded home point. The drone will ascend to a set return to home altitude and then fly back. While returning, it uses the GPS navigation and the obstacle sensors. When you press it again while return to home is in progress, it cancels the return to home, giving the control back to the pilot. On area 13 this is the power switch. If you press it once you can see the state of the battery, and if you press and hold it, it will power up the controller. In area 14 we have the USB-C communication port, and this port is used to connect your mobile phone. When the drone compresses its camera feed using the H.264 or H.265 protocol, it will send that signal back using the OcuSync. Once the video feed comes back, it will go to the USB-C communication port. From there it will go to your phone where you can see the live feed image from the drone. The remote controller cable is connected to this port in location 14. This connector here is the primary connection to your phone or tablet using the data cable. So the communication between the drone and the phone is done at this communication port. And you can also flash the firmware updates using this communication port. So you can update the controller using your mobile phone. The battery indicator LEDs are located in area 15. We have 4 battery indicator LEDs, so 1, 2, 3, 4. The battery level indicator on the controller uses LED lights to show the current battery status. If you have 4 solid green lights, the battery is fully charged. If you have 3 solid green lights, the battery is around 50%. If you have 2 solid green lights, the battery is around 25%. If you have 1 blinking green LED, the battery is critically low, so it is less than 12.5% charged. So basically these LED indicators help you monitor the battery status. These 2 antennas are used for the OcuSync digital transmission system. They transmit and receive the signals between the controller and the drone. These 2 antennas are located in this region, number 16. The controller got 2 antennas. These antennas are used for the OcuSync digital transmission system. The antennas are needed for stable video feed and send control signals over long distances. The controller uses 2.4 GHz and a 5.8 GHz frequency band for the communication. This dual band capability helps in maintaining a good connection between the controller and the drone. The 2.4 GHz antenna has a higher reach compared to the 5.8 GHz antenna. That is because the 2.4 GHz band has a longer wavelength, which allows it to travel further distances and penetrate through obstacles like walls and trees. The 5.8 GHz band has a shorter wavelength, which limits its range. It can get more interference from physical obstructions. But the 5.8 GHz frequency band offers faster data transmission speeds and is best suited for shorter distances and open spaces. The battery charging management chip is located here, is the BQ24259. This chip is responsible for generating the system voltage that will go to different chips on the mainboard. And this chip is also responsible for charging the Lipo batteries. Power management chip is located in area 17. This chip is in BQ24259. It's a switch mode battery charge management and system power management chip. This chip is responsible for charging the 2 Lipo batteries. It supports charging up to 2 amps. This chip is also responsible for generating the system voltage of 4 volts. And this 4 volts will deliver power to the different components on the main board. At the same time, this chip will also charge the Lipo batteries. Only if the power supply that is connected to the USB-C port, then this power management chip will charge the Lipo batteries. It will start generating the system voltage of 4 volts. In this chip there are safety features such as over voltage protection, over current protection, thermal regulation and battery temperature sensing. This chip communicates with the microcontroller using the I2C interface. This allows the microcontroller to monitor and control the charging process, adjust the settings and read the status of the battery. This chip is also connected to the battery and it will manage the charging and discharging cycles to the battery. This chip also manages the power input from the USB-C port. It will regulate the charging current and the voltage according to the USB standard, also known as the power delivery protocol. So the output system voltage is 4 volts and the output resistance should be higher than 10 kilo ohms. And in red are the diode measurements. This chip is the communication processing chip. It is connected to the S1 signal processing chip and also to the 5 GHz frequency band power amplifier and the 2.5 GHz power amplifier. This chip is located at region 18. This chip is a Leascore IE1000 and it is used for the OcuSync digital transmission system. So this chip acts as a 5.8 GHz radio frequency front-end transceiver. So it's handled both power amplification and also low noise amplification. So this chip will create a strong and clear signal that will be transmitted to the antennas. This chip is connected to the S1 signal processing chip and also to the amplifiers. So this chip is a 5.8 GHz radio frequency front-end transceiver. RF stands for radio frequency. That's a type of signal that the drone uses to communicate with the controller. The front end means it's the part of the circuit that directly handles sending and receiving the radio signals. And the transceiver means it can both transmit, send and receive the signals. Think of this chip like a tiny post office for wireless signals. The controller wants to tell the drone where to go, and this chip converts the digital control signals from the microcontroller into a 5.8 GHz radio signal and sends it through the antenna. When the drone sends back telemetry like battery level, GPS data and the camera status, this chip receives the 5.8 GHz signal and converts it back into a digital data the controller can understand. So this digital data will be sent to the microcontroller. This chip communicates with the microcontroller and also with the front-end transceiver chip. The S1 chipset is located here. This chip is responsible for a good data connection between the drone and the controller. The S1 chip is part of the OcuSync system, which is responsible for the high-speed, low-latency communications between the drone and the controller. It manages the radio frequency protocols, including the signal modulation and demodulation. The S1 chip is connected to the Leascore IE1000 chip, and it acts as a radio frequency front-end transceiver. And the S1 chip will also communicate with the microcontroller. This ARM Cortex microcontroller is basically the brains of this whole operation. This microcontroller handles the control signals, the sensor input, the signal packet creation, so basically the instruction what the drone has to do. It is responsible for the USB communication between the smartphone and the drone. And it's also responsible for the OcuSync transmission system. So this Cortex ARM processor handles the processing of the control signals from the joystick and other inputs. It is responsible that these commands are interpreted and executed by the drone using the OcuSync digital transmission system. This microcontroller is also responsible for the power management, the battery monitoring and firmware execution. So when we zoom in, this is the Cortex ARM processor. So the Cortex ARM processor handles the processing of the control signals from the joystick and other inputs. The commands are interpreted and executed by the drone. This ARM processor also handles the communication protocols, like the OcuSync digital transmission system. This involves encoding and decoding the signals between the controller and the drone. The processor will also do some different tasks like power management, battery monitoring, the firmware execution. The microcontroller also accesses the flash memory to load and execute the firmware. So to summarize, if you move the left analog stick, this microprocessor will detect it. It will generate a digital signal. From here, it will process these signals and will interpret this command. And these commands will be sent to the drone using the OcuSync transmission system. In region 21 and 22, we have two chips which are responsible for the amplification of the signal that has to be transmitted to the drone. So these two chips are low noise amplifiers and power amplifiers, which are used to boost the signal before transmitting it to the antenna. One chip will boost the signal for the 5 GHz frequency band, and the other chip is responsible for boosting the signal for the 2.5 GHz frequency band. The two power amplifier chips are located here. One chip is missing because I was repairing this mainboard. So normally there would be a power amplifier chip here. The value in red are the diode measurements. I measured it with the repaired mainboard, so the chip was present here. The chip that should be here is called the QPF4550, and this chip is an integrated front-end module and is designed for Wi-Fi 6 systems. This chip includes a 5 GHz power amplifier that boosts the signal strength for transmission, so this will create a strong and clear communication over Wi-Fi. This chip includes an integrated filtering for the third and second harmonics, as well for the 2.4 GHz frequency band. The main purpose of this chip is to route the 5.8 GHz signals between the two antennas. So this transceiver chip will basically select which antenna to send and receive data. The same applies to this chip, and this chip is the QPF4206, and this is also a power amplifier and a low noise amplifier. The main purpose is to amplify the outgoing radio frequency signal before it reaches the antenna, and it can also boost the received signal for better sensitivity. So basically this chip will select which frequency band to send the signal to. On the mainboard we have a buck controller, and it will create +5 volt. The +5 buck controller is located in region 23. This chip here is responsible for generating the +5 volt. This +5 volt is used to power different components within the controller, such as the microcontroller, communication modules and sensors. This voltage rail will also go to the power amplifier chip that we saw in the previous sheets. If you have a controller which doesn't turn on, so there's no reaction at all, you don't see lights and anything, check this voltage rail if it is shorted. Because if the controllers are faulty, most of the time it's because there is a short on this voltage rail. And the cause of the short is most likely one of those power amplifiers that is shorted. So this chip was faulty, I replaced it with a new chip and everything was working fine. When the voltage rail is shorted, check all the components that needs those voltages. I have analyzed and explored the DJI RC231 controller from the USB charging and flight mode switches to the 5.8 GHz transceiver. Also the microcontroller and the radio frequency chips that keep your drone connected. If you'd like to buy and download the presentation with the diode measurements, please check the video description below. Every purchase helps me to support the channel and invest in more analysis and content for you. In the next video I will analyze this main core board of this Mini 2 drone. If you enjoyed this deep dive, make sure to like, subscribe and hit that notification bell. Drop a comment below if you have extra information. Until next time, bye bye.